Hello everyone and welcome to our first week in our virtual classroom. So as I mentioned on the Zoom call the other day, we are going to begin with topic 5, moving slowly with one section at a time. So this week we will be beginning with 5.1, nth roots, radicals, and rational exponents. So the supplies that you'll need for today is a writing utensil, and I hope you all have your math notebooks. Of course, as you know, I won't be able to necessarily grade your notes because I don't really have a way for you to get them to me. However, this information is still going to be very important to you, not only in this math class, but in future classes as well. So I would highly recommend you continue to take notes so you have something to reference, especially when doing your homework assignments. So our learning target for today, I can relate roots and rational exponents and use them to simplify expressions and solve equations. I realize that we are not in a classroom, but if you are an organized person like me, I would want to continue to label my notes the same way that we've been doing it just to stay organized. So our heading for your notes for this section, 5.1, nth roots, radicals, and rational exponents. Now would be a great time to go ahead and pause this video to give yourself a chance to write down the heading of your notes. Otherwise, we are going to continue to move forward. This chart, ideally if we were in the classroom, I had a printout for you so that way you could just glue it right into your notes. Unfortunately, I don't have the power to get those papers to you, so you might want to write these down. These are going to be incredibly important to you throughout this entire chapter. This entire chart with these 3 rows are basically going to be your cheat sheet for all of the problems that you complete. So the first row is a list of your perfect squares. These are the numbers that you can take the square root of and they come out evenly in a whole number. The next row, perfect cubes. So that's when you take a cubed root of a number and it comes out evenly in the form of a whole number. And the last row, perfect fourths. This is when you take the 4th root of a number and again it comes out evenly in the form of a whole number. Again, this chart, I would highlight it, I'd circle it, do something. This is incredibly important. That's why we start off this section with it, because you're going to need it for the. Now that you have the table of perfect squares, cubes, and fourths, we will move on to discuss the parts of a radical. Again, this is supposed to be a glue-in part of your notes to alleviate some of your writing, but unfortunately we are going to have to make do with the resources that we have. So to begin, we have a few different pieces of a radical. We have the nth root of a real number, a, can be written as the radical expression, as shown on the slide. The first part that you're going to want to know, n is what we call the index, and that is the little number that is on the outside of the root. Obviously, we know that when n is 2, we don't typically write it there. We really only see it if it's a number greater than 2. Next, you'll be familiar with the radical sign. And then finally, a is what we call the radicand. If there's no index, it is assumed that n equals 2, like I just mentioned. Something else that I want to add is that sometimes you'll see that the radicand, the letter a, is sometimes raised to a power. And that's in the place of m that you can see on the screen. So now we want to talk about exponential form. And this right here is what we call exponential form, where you have your radicand or your coefficient, and then you have m and n. Those are both raised into a power. I know it's kind of hard to see, but they are raised in a power. So m, again, is on top over your index. So everything just kind of slides around. After talking about the parts of a radical and looking at exponential form, we are going to try the next 2 examples. It says, convert the following examples between radical and exponential form. Give me a moment to transition to. Now that I have the document camera up, we will take a look at our first example. We have 5 raised to the 6/3 power. It is currently in exponential form, and we want to be able to change this into radical form. The first thing that we need to do is identify the pieces parts we have in front of us. In blue, we have the radicand. In red, that was the placeholder for letter M. And in black, we have our index. So we, like I said, want to change this into radical form. To do that, I'm going to put my index on the outside and then I'm going to draw my radical sign. Next, we are going to go ahead and list our radicand, which we said was in blue and is the number 5, and then the m stays exactly where it was. And that would how we change something from exponential to radical form. Looking at our next example, this one is in radical form this time, and we have to change this to exponential form. So again, we identify the pieces parts. The 4 is the index, the 7 is the radicand, and 2 is that letter m, that placeholder for the exponent. So if I wanted to go ahead and change this, I'm going to keep my radicand as the big number. I'm going to put my 2 in the m spot in the top, and then on the bottom, I'm going to go ahead and list my index. Even though 2/4 could be reduced, I'm not going to reduce it. I'm going to leave it as exactly 2/4 the way that you see it. Later, when you go to complete your homework, you're going to come across some questions that ask you to list the amount of possible rational solutions. This chart is going to be a cheat sheet to help you get a very quick and accurate answer. The first row that we're going to look at is when you have an even index and a positive radicand. So an even index, that would be like a square root or a 4th root or a 6th root or something like that. Positive radicand means that your number is positive, not negative. So when you have an even index and a positive radicand, you are going to get a real root, but you're going to have 2 of them because you're going to have a plus value and a minus value. So that means if you are trying to take the square root of 25, okay, it's an even index and it's a positive radicand, you would get plus or minus 5 as your list of possible real solutions. Next row, when you have an odd index, so that's a cube root or a 5th root, and you have, again, a positive radicand, your answer is still going to be real, but you're only going to have one positive solution. Next, this would be when you have an odd index. So again, a cube root or a 5th root, but this time your radicand is negative. Again, your answer will be real. However, your root is going to be negative. And finally, this is the only case that you have an imaginary root. When you have an even index, so a square root, 4th root, but your radicand is negative, you will still get 2 answers. They'll be positive and negative, but they will be considered. These next 4 problems that you see on your screen are an excellent example of the type of questions you will see on your homework. It says, give all the possible roots for the radicals shown below. I hope that you wrote down the chart on the previous slide so that way you can go ahead and answer these questions easily. Give me a moment to transfer again to the document camera so we can do these problems together. Now that we have our document camera working, we are going to go through these next 4 examples together. First, we have to identify if the index is even or odd. Then we have to identify if the radicand is positive or negative. Looking at this first one, since it is squared, since there's no index visible, we have an even index and a positive radicand, which means that we are going to have 2 real solutions. You go to your calculator now and you take the square root of 16, you are going to see that you should get positive and negative 4 as your answer. Next, we're going to go right below it. We have the cubed root of 343. As you'll see, we have an odd index, but again, we have a positive radicand. This means that we will get 1 real solution and it's going to be positive. If you take a moment to put this into your calculator, you are going to realize that you get positive 7 as your final answer. Next, we're going to move to this one up here. We have the cubed root of negative 125. If you look at your chart, we have an odd index, but this time we have a negative radicand. So in this case, you're going to get negative 5 as your final answer. This one down below, it looks a little bit challenging, but don't think of it as any different than the other ones. In fact, we can write it similar to how we wrote the other ones. We can write the 4th root of 81 divided by the fourth root of 16, and then proceed as normal. If you take the fourth root of 81, you have an even index and a positive radicand, so how many answers should you get? If you are thinking 2, you are correct. You will get plus or minus 3. And on the bottom, again, positive radicand, even index, you'll get plus or minus 2. Now, of course, you don't really need the plus or minus on both the top or bottom since they are the same. So we could just simply write this as plus or minus 3 over 2 and leave it just like that. The next thing that we want to talk about in our notes is simplifying non-perfect roots. So these are the steps. Step 1, find the largest perfect square, cube, or fourth that the radicand is divisible by. Break down the radical using this number. Obviously, we can't exactly pinpoint if we are going to find the largest square, cube, or fourth until we know which one we're dealing with. And you'll see more of that as we get to our examples. Next, take the square, cube, or fourth root of the perfect number. Take it out of the radical. Once you take the square, cube, or fourth, the radical is gone. Like if you take the square root of 9, you know that it's 3. So you wouldn't continue to write that radical sign over the 3 because you've already taken the radical, just as an example. Next, you leave the leftover under the radical. So anything that you could not simplify, if you could not take the square, cube, or fourth of that number, then leave the radical sign there because you didn't do anything to it. I will give you a minute to write down these examples. But these are the examples that we're going to go through together so you can kind of see exactly how to simplify non-perfect roots. All right, we are going to look at those examples that were previously shown on your screen. These examples, we are going to use the steps of simplifying non-perfect roots. You look at the example on the left, the square root of 32. We must use these steps of simplifying non-perfect roots because if you were to try to take the square root of 32, would not come out perfectly as a whole number. So step 1 says find the largest square, cube, or fourth that the radicand is divisible by. Well, in this case, we're going to find the largest square that the radicand is divisible by because our index is 2. As you can see at the top of the screen, I have my chart of perfect squares, and this is where it's going to be very helpful. I have to find the largest number in that row that I can divide 32 by evenly. And remember, it has to be the biggest number in that row possible. Well, I can skip past 1, I can skip 4, and I can skip 9. However, 16 is a good number to stop on because that's the largest number that 32 can be divided by evenly. Then I'm going to write it as shown below. I'm going to branch off. I'm going to write it as the square root of 16, and then 16 times what equals 32? Well, in this case, it's 2. I have to keep the radical sign because I've not taken the radical of either number yet. Now, step 2 says take the square root of the perfect number, take it out of the radical. So we said that 16 was my perfect square. So what is the square root of 16? I hope you all said 4. Again, take it out of the radical. Then it says leave the leftover under the radical for step 3. Well, we can't take the square root of 2, so I'm going to leave it just like this. And that is my final answer. Next, we're going to look at the the right-hand side. This one looks a little bit different in the fact that it has a 2 out in front. It's not going to change our steps. In fact, I'm going to copy down the 2 below it exactly as seen. And I'm not going to worry about it right now. Next, I have to break the cubed root of 432 down exactly the way I broke the example down on the left. This time I have to find the largest cube that the radicand is divisible by because of the index. So we have to find the largest number in this middle row here that 432 is divisible by. You could try and divide those out. I am going to speed it up for you and tell you that you can divide 432 by 216. So I'm going to put my multiplication sign and then break it down. So I have the cubed root of 216 times 216 times what gives me 432? Well, in this case, it's 2. We continue our steps from the last problem. So take the cubed root of the perfect number, leave it out of the radical. Bring down the 2 that was already there. What is the cubed root of 216? Should be 6. Then leave the leftover under the radical. So again, we can't take the cubed root of 2, so we leave it alone. Then you combine whatever is outside of the radical. So I can combine 2 and 6, I can multiply those to give me 12, and rewrite what is still left within my radical. This would be my final answer in this case. These next two triad examples are continuing the use of simplifying non-perfect roots. I would like you to try these on your own and then continue playing the video to check your answers. We have finally made it to the last section in our notes. Section 3 is talking about roots with the variables. So how do we take a root of something when there's a variable inside the root? This is an example that will help you walk through it. So in this given example, you have the square root of your radicand raised to an exponent. So your index is 2. So if m is a multiple of 2, use the rule as shown up there. So you divide m by 2. If m is not a multiple of 2, break it apart. So you subtract 1 from m and multiply it by your radicand. You will see more examples of this as we proceed through the slide. This is an example of when you have a third root. These rules continue to apply. You just have to adjust them depending on what your root is. So if m is a multiple of 3, use this rule. Very similar to the rule shown above. If m is not a multiple of 3, break it apart so that it is. These are the two examples that we are going to walk through together so you can have a better understanding. All right, looking at our examples as shown on the paper and as shown in the previous slide, we are going to walk through these to see how we take roots with variables. If we look at the example on the left, we'll notice that the index is 2. Which means that we are using the given scenario at the top. So if m is a multiple of 2, use this rule. So 5 is in the spot of letter m. Is that a multiple of 2? Can I multiply 2 by anything to get 5? I hope that your answer was no. So to do this, we have to break it apart. So if m is not a multiple of 2, we have to take m minus 1. So what is 5 minus 1? Should say n to the 4th, and then multiply it by what's left over. I could put a little 1 right here. It doesn't matter, it's not going to change anything. We know that if there's not anything next to your coefficient, that there's an imaginary 1 there. So again, what we did was we broke it apart. We did 5 minus 1 to give us 4. And then we have whatever we took out on the left side and what's left over on the right side. We did this because similar to our examples previously, we can take the square root of n to the 4th evenly. And if we do that, we would end up with n squared, because 4 divided by 2 is really 2. And then multiply it by whatever we have left over. And this would be my final answer. Looking at this one, again, my index is going to be 2. So can I take the square root of 25 evenly? And I hope you would say yes. So on the left side, I'm going to have 25. Looking at our number 6, is 6 a multiple of 2? Again, you would say yes. So it's going to come with it. Then we ask ourselves, is 13 a multiple of 2? And we would say no. So we have to use our scenario where we do 13 minus 1. So we would get y to the 12th. Now we have to account for that one y that's left over. So we're going to multiply it by the square root of y. Now in this left side, this is everything that we can take the square root of evenly. So the square root of 25 is 5. And then we have our variable x. 6 divided by 2 gives us 3. We have our y. 12 divided by 2 is 6. And we leave whatever we had left over. We can't do anything to it. So in this case, this would be my final answer. We have finally made it to our final examples. Go ahead and attempt these problems using the roots with variables steps, and we will check them on the document camera momentarily. Now that you've completed topic 5.1, reference the homework assignments listed on the screen in front of you. You have one Edulastic assignment. This would have been your textbook problems. Obviously, we cannot do textbook problems, so please complete this assignment on Edulastic. It is due Saturday, April 11th by 9 o'clock. The second assignment you will be responsible for this week will be 5.1 online problems on Pearson. We would have normally done this had we been in the classroom. Again, these will be due Saturday, April 11th at 9 p.m. Please email me if you have any further questions.